Okay, good morning, everyone. So what I'm going to do today is actually give an introduction into what density functional theory is. So there's actually very little in terms of practical application, practical calculations we'll see today. That might be something where we want to have another talk. So let's just dive in, and you'll see in the name of what we are thinking about density, we know charge density, electron density theory, we know what is a functional. What is a functional? So we know a function maps a number into another number. So we go just chosen here the real numbers, but it might be any type of numbers to another one. So for example, x squared is a function. If we take f of 1/2 for f equals x squared, we get a quarter. So we're all familiar with this, and we know how to do differentiation, integration, all that fun. But what now a functional is actually a function of a function. So a functional maps a function into a number. So we can formally write it as something that takes a function from the real numbers to the real numbers into a real number. So one example of this would be a definite integral, for example. I have here a function, a functional that is just the integral of an arbitrary function from 0 to 1. So this functional of x squared, for example, would be now 1/3. If we put in a different function, we get a different number. So another thing that we'll need is a functional derivative. So we want to know how a function now changes in the neighborhood of a given function f. That means for any arbitrary infinitesimal change of a function f, which we write with a lowercase delta f, which is defined as an infinitesimal number epsilon times an arbitrarily chosen function eta. How does this functional of f change? This functional derivative delta f over delta capital F over delta lowercase f is actually defined so that this integral over the derivative times this probing function eta is the same as the derivative of now the function that is defined, as you see on the right-hand side. So if you have a function now of f plus epsilon eta, this is actually now a function of epsilon. So the derivative of this function capital F of f plus epsilon eta d epsilon at epsilon equals 0 is basically the definition of the functional derivative, if that holds for any arbitrarily chosen function eta. In practice, one can actually quite often get away with choosing the Dirac delta function as eta. So what are we going to do? So we start out with the many-body quantum mechanics Hamiltonian that we are using in things like condensed matter physics, material science, chemistry. Basically, every time we need to deal with nuclei and electrons, we have this general Hamiltonian. So we have the kinetic energy of all the electrons, the interaction of the electrons, the kinetic energy of all the nuclei, and the interaction between the nuclei, and finally the interaction between the nuclei and the electrons. So lowercase r are the electron positions, uppercase r are the nuclear positions, and the z's are the nuclear charges, and the capital M are the nuclear masses, and lowercase m is the electron mass. So if the Hamiltonian is time invariant, as the one we've just written down, if we don't have an external field, it is, we can in principle find the solution of the time-independent Schrödinger equation, which depends on all these coordinates. Depending on the electrons are for sure fermions, so you'll have to make sure that you have the proper antisymmetry behavior if you change positions, and similarly. So if we now assume that so that's a huge problem. So how can we reduce it? First thing is we can assume that the nuclear masses are significantly larger than the electron mass. And thus we can neglect the nuclear kinetic energy term and decouple the solution of the electron wave function from the nuclei. So we basically end up with an equation where we just have the kinetic energy of the electrons, interaction of the electrons, and then an external field that comes from the nuclei. So now we only really need to find the solutions for the electron wave function, which is a function of n coordinates, basically going from r to the 3n into the complex numbers. In principle, we know how to numerically solve this equation, but there is a problem of dimensionality. Just consider the memory requirement to store a wave function like this. If we tabulate this for just 1,000 points for each of the electrons, which actually is just a 10 by 10 by 10 division of a space, so really, really low resolution, and store a double complex number, which is 16 byte for each of these points, one electron, say for a hydrogen atom, say, is really no problem. We only need 16 kilobytes for that. We could have stored that on a 1980s personal computer. 2 electrons will need 16 megabytes. That probably takes us 2 decades from the 1980s to the 2000s. 3 electrons. If we want to deal with lithium, we need 16 gigabytes of storage. Still doable. If we just have 4 electrons, beryllium, we already need 16 terabytes of storage. So order of magnitude, 1 large hard disk. A carbon atom, 6 electrons. Nothing really very exciting going on here yet in terms of chemistry or material science. Would actually need 1,000,000 times more than we needed for the beryllium. So 1,000,000 large hard disks just to store the wave function. So in general, you see that just the memory requirement grows exponentially with the number of electrons. And as the memory grows exponentially, we know that the computing time also has to grow exponentially, just assuming that we will have to touch each of the memory locations at least once during a calculation. So a brute force direct solution is definitely not feasible. There are different ways of how to tackle this, how to cut down the space that needs to be sampled, like quantum Monte Carlo methods, or various quantum chemistry methods. But the probably most popular and widely used approach of dealing with this is density functional theory. And that basically starts out with this paper from 1964 by Hohenberg and Kohn, which actually shows that at least in principle, you don't need the full wave function, but actually can get away just with the electron density. So let's consider the electron density, which is actually just the charge density distribution within a system. You see, you actually get that by integrating out n-1 of the coordinates of the squared wave function. And the Hohenberg-Kohn theorem now shows that there's actually bijection between the external potential and the electron density, and also consequently one-to-one relationship between the wave functions and the densities. It is quite obvious that different densities have to be originated from different potentials. So one direction of the bijection is really trivial, but it is certainly much less intuitive that different potentials actually have to lead to different densities. And that's actually the genius in the Hohenberg-Kohn theorem. So assume that we had 2 different potentials, V1 and V2, that could lead to the same density. So if we have the 2 Hamiltonians, H1, H2, and their difference is because the electron part, and the kinetic energy part, and the electron-electron interaction part of these Hamiltonians are the same. The difference between these Hamiltonians is just the difference between the external potentials. These 2 Hamiltonians will have 2 different ground state solutions, and these capital Psi's are the many-body wave functions. So there's Psi1, which is the solution for H1, and Psi2, which is the solution for H2 with energies E1 and E2. And by our assumption, both psi1 and psi2 actually lead to the same density n. So as we know, that the Hamiltonian consists of both the kinetic and the electron interaction term plus the external energy terms. And if we write down the expectation value of these for a given wave function, we have this. And it now follows that for Hamiltonian H1, the expectation value of H1 under psi1 is the ground state energy, E1. So if we look at the expectation value of H1 under a different wave function, in particular psi2, which by our assumption leads to the same density, but for a different Hamiltonian, and this obviously has to be higher energy because it's no longer the ground state of H1. So we find by by rewriting H1 as H2 minus V external of V2 plus V external 1, that E1 plus this integral over the difference of the energies and where the density has to be strictly larger than E1. And equivalently, we can do the same procedure with the Hamiltonian H2 and find that E2 has to be strictly smaller than E1 plus the difference of the external potentials now with a reverse sign. And you see where this leads. If we add these two together, we find that we have two external potentials that give rise to the same charge density. We have this strict inequality. E1 plus E2 has to be strictly smaller than E1 plus E2. So this is definitely a contradiction. So we cannot have two different external potentials that lead to the same density. So this basically proves the other direction in this bijection, and therefore we know that there's a one-to-one mapping between the external potential and the resulting charge density. As a consequence, basically any observable can be written as a functional of the density of where we have a universal functional Fn, which is contains the kinetic and the electron interaction energy, and a material specific term that comes from the external potential. And in a sense, this is a nice proof, but not very practical yet, because by saying that anything can be in principle written as a functional of the density just means at this level, after we've proved the Hohenberg-Kohn theorem, is that from a given density we can go to the external potential and in principle reconstruct the many-body wave function from which anything can be solved. So we need a bit more ingredient to actually have something that can be practical. So approximations to the exchange correlation functional. So for practical application, we actually usually split this universal functional f into different terms. So we have the kinetic energy term, the Hartree or Coulomb energy term, which is basically the electrostatic energy of the charge density with itself, and then exchange and correlation terms, which contain basically all the many-body effects that come from the fact that we're dealing with fermions, and also that we have actually a overcounting of interaction in this Hartree term here, because it also contains interactions with electrons interacting with itself. There is actually a small number of methods that fall under the orbital free density functional theory method category that try to find the stationary density n that minimizes this functional. So you could directly find n by minimizing this Hohenberg-Kohn functional down here. And one of these approaches you actually might know and remember is actually significantly older than the Hohenberg-Kohn theorem itself, and that is Thomas Fermi theory from the 1920s, where you replace approximate Tn by the kinetic energy of non-interacting electron, homogeneous electron gas, and completely neglect the exchange and correlation energy terms. It's a terrible theory, but it is actually the very first density functional theory, even though Thomas and Fermi didn't know that it was ultimately exchange density functional theory. So how can we actually practically solve this? One of the great challenges, if you wanted to do orbital free DFT, is actually finding a good functional for the kinetic energy. The main ones that are around are the Thomas Fermi kinetic energy and the von Weizsäcker kinetic energy, which are basically the two extremes of homogeneous electron gas and perfectly bound electrons. So for most materials, you're actually somewhere in between, and there's significant research ongoing in how to construct better kinetic energy functionals, because if we had good working orbital free DFT, this would be a very well scalable method, because it really depends only on the density. So for practical methods, the huge majority of all DFT calculations actually based on what Kohn and Sham did in the paper that came out about a year later in 1965. And that is to actually take a slightly different approach to solving the problem. So realizing that really the main difficulty in solving many body problems arises from the electron-electron interaction. How can we go and get rid of this? So really the exponential growth of the n electron system comes from the interactions. If we just had n non-interacting electrons in the system, we actually could solve the system in linear time. We only have to find the n lowest eigenstates and stack them up in the case of fermions. So the question that is asked here is, can we find a non-interacting system that results in the same density as the interacting system? If we had these non-interacting single electron auxiliary electrons, in a sense, Kohn-Sham orbitals, and now lowercase phi I, we could write the energy of the system as now the sum over the single electron kinetic energies. So there's still a small error there in terms with regard to the actual many-body kinetic energy, but it is really tiny compared to the error in the approximations one needed to do in orbital free DFT. The external interaction with the external potential, the Hartree term at the end, and then the exchange correlation energy term, where we basically again sweep everything under the carpet that we hadn't included there before. Now the charge density is just the sum of the contributions that comes from the lowest lying electron states of this auxiliary system that we're going to find. And I'm not going through the derivation of the Kohn-Sham orbitals, but basically you're constructing an Euler-Lagrange equation that satisfies the condition, and you arrive at the end that looks, for all intents and purposes, like a one electron Schrödinger equation. So we have the kinetic energy term, and then this Kohn-Sham potential term. Now, what are the potential terms that enter here? We have the external potential. We have the Hartree potential. And finally, the exchange correlation potential, which is the functional derivative of the exchange correlation energy with respect to the density. Again, the external potential, the Hartree potential term, we know. Now, the kinetic energy we also know, so what is now left is finding in VXC. So if we were to know this exchange correlation potential, we basically finding the charge density and correspondingly all the energies and observables of the system amounts to finding the solution to a nonlinear eigenvalue equation. And it's nonlinear because this Kohn-Sham potential itself depends on the solutions here on the wave functions via the charge density. There exists many approximations for exchange correlation, for the exchange correlation energy. One of the simplest ansatz, and that is one that we've been using quite a bit, and that was originally already pointed to in the Kohn-Sham paper, is the local density approximation. So you write the exchange correlation energy as an integral over the charge density and a exchange correlation energy density, which only depends on the instantaneous point value of the charge density, and that in the LDA is taken to be the electron, the exchange correlation energy density of the uniform homogeneous electron gas. So how do we go about solving all this? We start with some initial guess of the effective potential of the Kohn-Sham potential. Use this to solve the Kohn-Sham equation, calculate the new densities, and then we compare the new results that we've got to our initial guess. And if we have not converged within the tolerance, we actually update the charge densities and effective potentials with the new one. Actually, in practical calculations, you don't take all of it. You introduce some mixing to avoid oscillations and to introduce fast and damped convergence. And this is basically an overview of what goes into density functional theory. Now there are all the details on how to implement it. There are many ways of implementing how to solve the Kohn-Sham equations, methods in expanding the solution in various basis sets, like in plane wave methods, or in our case in multiple scattering theory by actually finding the Green's function for the Kohn-Sham equation and then calculating densities from there, or solving on some type of grid using finite difference methods. And that is probably something that we can look at in a future talk, is what are possible exchange correlation potentials that are available and how can one solve. But this is basically the end of my overview of where does a density functional theory come from and how does it deal with a huge dimensionality problem of many-body electron physics. Thank you. So,
thank you, Markus. Yeah. So, any questions? It's a very nice talk. Good. That's very good. So for those not working in a abelition method, then I think this kind of really refreshing. You guys unmute yourself. Okay. Yeah. Let me stop the recording. So